Welcome to this FFT Sniffer feature spotlight for the Apollo MxFE. In aerospace and defense applications, spectrum awareness informs decision-making. Locate the energy in the spectrum to move to a clean frequency. The faster the better to gain tactical advantage. AD9084 Spectrum Sniffer is an on-chip FFT engine located after the ADCs to provide the user with low latency indication of where the strong and weak signals are within the digitized bandwidth. Inside a single Apollo chip, there are two instances of the FFT sniffer, one per side, A and B. The Spectrum Sniffer generates a 512-point FFT, the resolution bandwidth therefore being the sample rate, fs, divided by 512. It has a dynamic range of -1 to -25 dBFS for real data, and -1 to -31 dBFS for complex data. One pair of complex inputs from two ADCs or single real data from one ADC can be fed to each FFT sniffer instance per AB side. The MxFE crossbar is used to route the desired inputs to the sniffer. Any ADC can be fed in. The sniffer has two programmable thresholds, max and min threshold, that are used to conditionally determine if the data will be stored based on the signal levels present in the ADC spectrums. Operate the sniffer in one of four modes shown. In normal mode, the sniffer will store new data when the input falls within the programmed min-max threshold. Instant mode will store the data unconditionally, regardless of program thresholds. In magnitude mode, it will auto-calculate and store the magnitude of the input signal. It can be programmed to store only real magnitude data or complex magnitude data. Finally, in IQ operation, it will store data as in-phase or I data and quadrature or Q data. Taking a closer look at the FFT sniffer, the block contains various functionalities and hardware-based data processing options. All are options which the user can choose to enable or disable. The latency of the sniffer output data is dependent on the mode and settings selected. Operate in continuous mode to constantly store new data and guarantee the latest data is stored. Continuous is only available in magnitude mode. If disabled, the sniffer will be in single mode, where the data is only stored when the block is signaled to. Hence, the user may miss critical data. The signaling process will be detailed later. Add dither if desired to the input samples to reduce spurs across the spectrum. The sniffer has one top and one bottom FFT engine that are 50% overlapped and compute in parallel. The two engine results are averaged and help to avoid time domain events. There is a windowing option. A hard-coded Hamming window can be enabled to optimize for narrow spectral peaks. Exponential averaging can be enabled by setting the alpha factor between 1 and 8. Set it to 0 to disable. It sets the A value in the equation shown, so it directly controls the weight of the previous sample. It is only available in single mode and magnitude mode. The sniffer has a sorting option. If disabled, the data is left unsorted and is ordered by its bin number. If enabled, the incoming magnitude data is sorted from least to greatest. Sorting is only available in magnitude mode. Finally, a low-power operation is available. In order to lower the power consumption of the engine, it disables continuous mode and exponential averaging. The expected power savings when enabled is 600 milliwatts. To enable and configure the sniffer for data capture, the user can use the following API commands in sequence. First, enable a sniffer instance, A or B, using the function shown. Then, select the ADCs that will provide data to the sniffer. Set the data fields of the struct sniffer init, which programs the sniffer settings, and initialize those by executing the sniffer init function. Bring up the sniffer clocks by issuing a one-shot sync to Apollo. Then, the user can configure the remaining sniffer options like mode, averaging options, windowing, sorting, low power, and dither by populating the sniffer program T struct and executing function sniffer program. Now, the sniffer is set up and ready to capture data. There is a data request sequence to obtain new data after the sniffer is programmed. The data is stored in registers. Use HSCI or SPI to read the data from the registers, HSCI being the faster option, with a max speed of 1.6 gigabits per second. The user can choose to control the data request sequence by doing writes to the register map or toggling GPIO signals to Apollo. If using the register map as the control mode, the data request sequence is automatically handled by the API. In GPIO mode, the user needs to toggle the GPIO signals to request data. There are 3 signals: FFT enable, to enable the engine; FFT hold, to hold the overwriting of data to registers; and FFT done, which indicates that writing to the registers with data is complete. The GPIO toggling procedure is to first set FFT enable to high to enable the FFT. Wait for FFT done to read back high, indicating that the FFT is done and the data is stored in the registers. Finally, set FFT hold to high so that the data will be held in the registers and the user can read it. The latency of the FFT sniffer will vary depending on what mode and settings the user has chosen. Take an example with the device clock as 20 gigasamples per second, where each clock period is 1.6 nanoseconds. First, the data is captured taking 17 cycles. The FFT calculations take 30 cycles. Calculating the magnitude and averaging takes 19. And calculating the interrupt takes 2. The sorting and storing is 516 cycles. Therefore, the calculated latency would be after 584 cycles to get first data, or 934.3 nanoseconds at 20 gigasamples per second. If in continuous mode, the data will be updated every 16 cycles. If setting FFT enable low then high, add 66 cycles. If the user disables sorting, that will save 516 cycles to get data. Real mode sorting will only take 260 cycles since it is half the number of bins. This can be measured on our evaluation board. In an example measurement, the sniffer is configured in normal mode for real data. The sorting is disabled, and it is operating in single mode. Sample rate is 20 gigasamples per second, and the data request is done by GPIO to measure the timing from FFT hold going low to FFT done. Since the sniffer was already enabled, the expected latency is the data update time, which is 16 cycles, plus the propagation delay of the GPIO signal, which is estimated to be 25 to 30 nanoseconds. The total expected latency in this case is 51 to 56 nanoseconds. Measuring with the evaluation board over multiple runs, the max measured latency was below the estimate at 48.8 nanoseconds. Achieve fast frequency agility using Apollo's FFT sniffer and NCO frequency hopping, or FFH. The sniffer will locate the signal, and then the user can use fast frequency hopping to hop the frequency to a clean spectrum. The user's selected FPGA will toggle the FFT sniffer GPIOs to get data. Use HSCI as the fastest method to offload the bin data. After the user processes this information on their FPGA, select the new NCO profile using GPIO to hop the DAC side NCO. Expect the FFT sniffer latency to be 56 nanoseconds with it already programmed and operating in normal magnitude mode with real data in continuous disabled. The fast frequency hopping latency will be the GPIO propagation latency, plus the latency in the data path from the NCO to the DAC output. Overall, the estimated time to react is the sniffer latency with the fast frequency hopping latency, and the user's FPGA processing time, which includes the time to read the sniffer data with HSCI and the user's software processing. FFT sniffer example code is in the API example rxsniffer.c, or in the PyApp with example file fftsniffer.py. More details in the device user guide. Request software download via our product page on analog.com/AD9084. Thank you for watching this FFT Sniffer feature spotlight for the Apollo MxFE. Please visit our page for more information.